So next up we have Professor Brengt Lennartson from Chalmers University in Sweden. We'll let him get his laptop set up here. And we can switch the screen, I think. Got it plugged in? So someone up there, I think, needs to switch the screen. There we go.
Okay.
Okay, take it away.
So first, I want to thank the organizers who invited me to give this talk. And amazing to see all of you here. So I will not show you so many photos and pictures. I will more show you algorithm. And in the end, there will be 2 recommendations of 2 specific software, which I like very much. So maybe a bit technical, but I would like to discuss first very quickly on some models for discrete event systems and how they can be used for planning and scheduling by a specific software called CPSAT, and also some comments about robust reinforcement learning. So discrete event systems can be modeled in different ways, and we are familiar, I hope, everyone, about automata, Petri nets. Maybe not so much that we can also describe these by predicate transitions. So in this case, for instance, you have a buffer, and you have totally 4 states which represent occupied parts and 1 empty state. These predicates describe exactly the same thing as we see here in the automata and Petri net. And the thing is that the solvers we use typically to evaluate these automata and Petri nets are based on this type of predicate transition models. Okay, I will use a Petri net example where you can see here that you have typical 3 flows. Flow of parts. I assume that I have m parts in every initial place. And you see also I have 3 resources here, and they are related to these different sequences in a bit complicated way. So all these arcs, some people say that here you have the spaghetti of the Petri net. Here you have something which I consider as more readable. It's Petri net with shared variables, where the variables described here, R1, R2, the logics around these resources. So these models can now be used for planning and scheduling. And one very popular software is called SAT Solver, or Satisfiability Solver. It just tries to answer if a long, complex Boolean expression, if it's possible to satisfy that with a combination of the variables, or if it's unsatisfiable. And that has been used both in planning and formal verification. And how this works is simply a smart search. And I don't think I will take time to explain that more right now. I just go on to the next slide and actually evaluate this type of SAT solver for traditional planning. And in that case, it's simply that the SAT solver asks, okay, make 1 first transition. Have I reached the goal? If not, you try 1 more transition and ask, have I reached the final goal? And then you have to ask that question a couple of times until you have reached the goal, and then you have satisfied your goal expression. Then I tried one of the best SAT solvers for this, and I was surprised to find that actually already when I have only 5 tokens, initial tokens in each place for these 3 sequences, it took me nearly 450 seconds to solve this. At the same time, people say that the SAT solvers are the best for planning problems, but obviously not here. The problem is that we have quite deep many number of transitions before we reach the goal state. So then I will try another approach, which is from the beginning formulated for time optimization. And that's a combination of, also in this case, SAT, but also with constraint programming. And how can you use SAT for optimization? Well, you have a criterion, and you put the constraint on that criterion, and if that constraint is satisfied, then you reduce this number C here until you have pressed down so you cannot satisfy this constraint anymore. And then you have reached, one step backward, the optimal value of this constraint, of this criterion. And here you understand that we are only talking about integers all the time. Together with constraint programming, which also includes domain reduction and some very specific functionality, for instance, for scheduling, looking at non-overlapping, which means mutual exclusion and shared resources, and some special other filters. Then here I have an example of two series of production lines, and they are, after some time, joined. The PetriNet here describes this behavior, and this is really a hard problem, and I had long time very much difficulties to solve this. And then in the end I tried this CPSAT, and it worked, and it works extremely fast. So the question, could I also use this for the planning problem? And yes, actually it also works fantastic in that case. If I take the same problem as I had before with the more traditional solver, where I could only solve for 5 tokens in the initial states. Now I can do that in 5 milliseconds with the CPSAT solver. And I can go up to even 1,000 tokens in every initial state. So you see that it's a dramatic improvement, and my conclusion is just look at CPSAT and see what you can do with that. And the question is, of course, here, how could I use that? Well, the idea is that I use typically what is formulated in optimization. You have precedence relations, you have non-overlapping conditions, which you use for this purpose, to also describe these PetriNets. Also, some words about reinforcement learning. Well, I think all of you are familiar with reinforcement learning in the sense that you are trying to take a step forward and see what you can learn from that, and in the end also to reach goals in this case. The most popular one is what is called model-free reinforcement learning. And then you estimate both a criterion and a controller at the same time. It's very costly in terms of data, and it's a black box strategy. It's hard to introduce own knowledge. What I suggest here is instead to use a model-based reinforcement learning, where you first estimate a model, and then based on that model, you can choose any control design method you like. It's much more open, modular, and flexible. One thing I have also realized during the last year is that this model-free reinforcement learning is extremely sensitive to very high-frequency neglected dynamics, like an additional time constant in this case, which could be very small, but still it influences the performance or the stability of this robot model-free reinforcement learning in a very surprising way. At least the model-based version is clearly better. So in this case, as an example here, I look at eco-driving of a truck. And actually, in this case, the basic dynamic model can be formulated something like this. And it's more or less a black box because you take a polynomial in the velocity, you take a polynomial in the slope of the road, and also, due to Newton's law, you have a relation between the acceleration and the force of the torque. Nothing more. Very, very basic knowledge. The rest you can estimate by estimation tools, the parameters. Another thing now, when I have estimated this model, I can also formulate something very classical, a nonlinear feed-forward and feedback control strategy, also including anti-wind-up because I have restrictions on the control signal. The final thing here is that I also introduced something I called temporal optimization. And I will not go through all the details there, but the very basic idea is that from the beginning you have equidistant sampling periods of the trajectory of your problem. And if there are high accelerations at some points, then you increase the sampling period for that part. And some other parts where it goes slower, you can decrease the sampling period. And in that way, we can also solve optimization problems. And I will soon show you a movie with a robot where we have applied this. But first, I show you also some results for this eco-driving of the truck. And if you have the shortest limit of restriction going from place A to B, and you have these speed limits, the solution will go just to the speed limits. But if I get some more time, I can drive a bit slower and save energy. And it's also interesting to see here that in this case here, that the feedback works quite much here because I haven't given the information about the slope, but that is taken care of by the feedback loop. So here is a movie where we have tried this concept also for a robot, energy optimization. And here it comes the energy optimal one. The first one was just recorded the original motion. Here you saw both solutions overlapped on each other, and you saw that they were moving more or less all the same. But still, they ended exactly at the same time, and I got 20 to 25% energy reduction. And peak power, a reduction of even 50 to 60%. Quite nice result. A collaboration with KUKA and Daimler. Summary. Use CPSAT, or there is another alternative called Z3Opt for planning and scheduling. And use model-based reinforcement learning where you can combine nonlinear system identification, specifically with MATLAB's toolbox system identification, and take traditional concepts from control, feedback, feed-forward control, and also this more spectacular temporal optimization, and you can get very good results with few data. Thank you.
And thank you, Bengt. Are there any questions for the speaker? So I'll ask a question. How accurate do your models need to be in order for these systems to give you good outputs?
Yeah, it's an interesting question about accuracy. You could say that the estimation of these models with our data, with this nonlinear system identification toolbox are very good, but it's still sensitive to these additional dynamics if you happen to have that. So we tried with one just extra small time constant, and you can see some influences also with the model-based version. And remember then that traditional system identification is typically based on input-output models, but they are not natural for reinforcement learning. But what we are working now hard on is to also adapt this scheme so we can use these input-output models. And then you can introduce neural networks, wavelets, and all other types of nonlinear functionality to this framework.
Great, thank you. Is there another question? If not, let's thank Bengt again.
Thank you.